Hello, good afternoon to all. Welcome to this first doubt clearing session of the course, Engineering Thermodynamics. So what I'll be doing already, I have shared one Google Sheet with you all, which is accessible to all. So all of you can mention your queries there, and some of you have already put nothing but our surroundings. Okay, this point is clear.
Yes, sir. Thank you.
Okay, now next question is like what was the actual meaning of L you have used? So the L, whatever I have specified you in the formulation of continuum, that is nothing but it represents that what is our dimension of the system. For example, in this container case, if I take, then this entire length L is nothing but our characteristic dimension. For example, if I have a situation that flow is happening over a turbine, then what is happening? This is nothing but the schematic representation of a turbine where we will be having actually, sorry, this is wrong. This actually is for compressor. So if I have to represent a turbine, in that case, what I need to do, I have to basically, I'll be having some expansion of the fluid. So whatever fluid we are having over here, that fluid will be actually expanding from inlet phase, if I consider this as nothing but our inlet, to the outlet. Okay. So in this case, what will be happening inside, we will be having number of turbine blades over which our actually fluid will be actually expanded. Okay. And finally, we will be getting some work output out of this turbine. So in this case, you can see that whatever the length of the turbine we are having, that we can consider as characteristic length scale of our system. So am I clear in this point?
Yes, sir.
Okay, now someone has written in the chat that in which case do we take the container with its thick boundaries? So there are many cases. For example, if we are having a container and inside that pan we are heating water. Okay, so what will be happening? obviously we will be heating the outside surface of that container, and then heat will be transferring from container surface to the gas. So sorry, to the liquid water, whatever we want to heat. So in that case, we will try to consider. So it's up to us. If we want to study the behavior of water, then we will be taking only water as a system. If we want to see that how much change is happening in the temperature of the container also, in that case, we will be including container also as the part of the system. So am I clear in this point?
Sir, what is the difference between having a thick boundaries and thin boundaries? You said that it is just for demarcation. Then what is the basic difference between having a thick and thin boundaries of the system?
So see, there is no demarcation in between the thick and thin boundary. I am not referring the word thin and thick to the boundary. I am referring the word thin and thick to the type of the container. Boundary is something which is nothing but imaginary area which specifies that what portion of matter is under observation. Is this point clear?
Yes, sir.
So thick and thin is nothing but it is referring to the thickness of the container. So this I have taken as asked in the question. However, in reality, there is no meaning of thick and thin boundary. Boundary only represents the demarcation. So the idea is whether thickness of the container can be part of the system or not. So for that, I am explaining that if only we want to study the behavior of fluid, then only fluid will be part of the system boundary. And if we want to study the container material also as part of the system, then obviously container thickness will also be included in our system boundary. So is this point clear?
Sir, if we want to observe anything,
Yeah.
hello,
Yeah, please go ahead.
that it is in a system, right?
Sorry, can you
Sir,
repeat?
if we want to observe anything, then only
Yeah.
we can put it in our system, right?
Yes, yes, that's it. That's it. Whatever we want to study, that we will be putting inside our system boundary. Okay. Anything outside system boundary is not part of our observation. Should I go with the next question or anything else is there? Can I go with the next question?
Yes, sir.
So the next question is, sir, please explain once more about the time scale that you discussed in continuum. Okay, so let me once again discuss the idea of the time scale, whatever we have used. So what I have told you, in case of continuum, okay, one I have talked about length scale. Now the question is specifically on the time scale. So let me talk about time scale only. So what I have told you, as we know that molecular length scales will be of the order of, for example, diameter, etc. Size of the molecules will be of the order of nanometers or even small. Okay. Similarly, we will be having molecular motions. So what we are talking about, for example, if two molecules are colliding with each other. So the way I have shown over here, one molecule is moving towards right and second is moving towards left. So what will be happening? These molecules, after some time, they will be actually colliding with each other. Okay. So whatever the time scale we are having in between the molecular positions, that time scale is nothing but of the order of nanoseconds or even small. Okay. So that is first point. So obviously, when from a molecular perspective, we will be finding the change of properties. That change of properties at the molecular level is happening within the time scale of nanoseconds. Now, if we talk about, say, a gas contained inside a piston cylinder arrangement. So if we have a gas inside a piston cylinder arrangement, now this gas, if we provide heat, obviously what will be happening? Because of the heat, now this gas will be expanding. So whatever the time scale we will be having for the expansion of this gaseous medium, whatever we are having inside. So initially you can see this was the system boundary, and now this is our system boundary. Okay. So what will be happening in engineering scale? Whatever the change of system length scale will be taking place, or change in system property will be taking place, because if we are moving from this low volume V1 stage to high volume V2 stage, obviously the pressure and temperature of the system will be changing. Okay, so it means when we are moving from one state to another state in the engineering scale, system property or behavior is changing. So whatever the time required for change of that system behavior from one state to another state will be there. That will be nothing but of the order of seconds or minutes. Okay, so these processes either will be happening in few seconds or few minutes. So what we can do, we can say that if in our engineering scale phenomena is happening at second or minutes level, by that time in the molecular scale we will be having large number of molecular interactions, which will be giving us some time averaged bulk properties. Is this point clear? So should I go to next question then?
Yes, sir.
Yes, sir.
Can you repeat the statement of time average bulk properties?
Yeah, so what I am saying, that when in our engineering scale phenomenon is changing, it is requiring time of the order of seconds or minutes. Okay, so during that period of seconds or minutes, we will be having sufficient large number of interactions, because their order of occurrence is in the range of nanoseconds. Okay, so that's why whatever the change of property we will be experiencing at the engineering scale, that will be actually because of the large number of molecular interactions. So we can consider that over that period of engineering time scale, this change of property is nothing but representing the time averaged change in the bulk property. Am I clear?
Yes, sir.
Okay, so I am then going to the next question. Sir, please explain about time averaged bulk properties. Please give some link of the required course books. So particularly you can refer to this book by Wozniak and Sontag for this discussion on the molecular and macroscopic linkage in between the properties. Okay, so in its first chapter, they have actually briefly discussed about this particular thing. Okay, so bulk property, I think already now it should be clear to you. The idea is that at molecular level, we will not be having constant property everywhere. For example, if I talk about molecular level, so we will be having number of molecules. So in between molecules, we will be having large voids. So it means whatever the value of temperature I am having at this molecule, say it is T1. In this void space, obviously my temperature will not be T1. Okay. So in that case, what will be happening? We cannot say that everywhere our value of property is same. So, but if we talk about continuum, we consider that though we are having molecules, but molecules are very, very large in number, and our scale of the this system is so large that inside that large scale we are having large number of molecules. So because of the large number of molecules, whatever our now domain will be there. Everywhere we will be finding almost the occurrence of a molecule. Okay, so because of that, what will be happening? We will be finding that whatever the overall property of the system we will be getting, that is nothing but averaged over the individual molecular activities. So that's why we call that as nothing but bulk property. Am I clear? Okay, so one question is there in the chat box. Can you explain the term continuum? So as I have told in earlier lecture also, in our today's morning lecture also, that term continuum refers to the situation where at each and every location we are having homogeneity in composition. We are not having any void space. We are having uniformity throughout. Okay, so when we take the assumption of continuum, we consider that our medium is continuous and we are not having any voids in between. Yeah, it seems correct. No void assumption. Anything? So is this point clear? Shall I go to next question?
Yes, sir.
So I have a question. I
Yeah,
forgot to write it in the Excel sheet. Why do we in an open system, if the exchange of matter occurs, and why is it called volume controlled?
okay. Why it is called volume control? Okay. So basically what we are doing when we write the conservation, either we say that our system is mass conserved, okay, or we can say we are having fixed volume. So in case of fixed mass system, whatever the mass we are having, that will not be changing. However, in case of another type of system, because we are having inflow and outflow of the mass, so obviously mass of system will depend whether inflow is more or outflow is more. If inflow is more, in that case, there will be accumulation of mass within the system. If outflow is more, then there will be loss of mass within the system. Okay. So what ultimately is happening, our mass is changing. So we require something, a fixed boundary within which our actually change of the mass is happening. So that's why we try to fix the volume.
So, but if we take an open system in which we are heating, so the like we have water and it will
Yeah.
evaporate, so the volume will also change.
Yes, it may happen. It may happen. That's not a problem. See, the idea is what we want to do, because we will be having mass if we are having the change of both mass as well as volume. Okay. So in that case, what we will be doing from analysis point of view, it will be difficult to analyze the system. We can have in reality a system where our inflow and outflow is also happening, and at the same point of time, boundary of the system is also changing. Okay, but in order to analyze the system where we are having exchange of mass, because of the theoretical constraints, we try to fix the volume. This point is clear?
Yes, sir. Okay. Thank you.
Okay, so
So
now
in case of a
yeah,
closed question to same, in case of a closed system, if we fix the boundaries, then in that case also volume is gonna stay fixed. So why not a volume control system?
So yes, closed system is nothing but once again a control volume having fixed mass. You got my point? So closed system
Yes,
is
sir.
a
Where
special.
mass is also fixed and in open system mass may vary.
Yes. So closed system is a special case of control volume with fixed mass. So more general term is nothing but our control volume. Point is clear?
Sir, energy may change in a closed system.
Energy may change. Energy may change. There may be energy interaction across the boundary, and mass will be constant. Okay, so then I am taking the next question from the Excel sheet. So what we have now, our next question is why we have not considered voids in macroscopic analysis, why it is required. So am I clear? I think this question already I have answered. Am I clear, or do I need to answer this? Asutosh, can you please, if Asutosh is there, do I need to answer this question, or is it clear now?
No, sir, it's clear.
Okay. Now next question is, what happens if L is very large in comparison to lambda? Okay, so that let me once again explain, though I have already explained, it should be now clear to you all, but let me once again quickly explain it. So what we are considering, as you see my previous figure, if say this is my lambda, okay, so you can clearly see over here, if this is my lambda, can you see lambda? I have written it on the board.
Yes, sir.
Sir.
So let us consider if this is my lambda, okay, and this is L. So now what will be happening? Whatever the comparison between L and lambda we are having, because of that, our molecules will be having arrangement something like this. So where lambda nothing but represents the average distance traveled by molecules between the successive collisions. So if I consider my L close to that of lambda, means L of the order of lambda, so in that case what will be happening? I will be having significant amount of void gaps in my system. Is this point clear? However, if I have my L as very large in comparison to lambda, so because of that, what will be happening? My molecular gaps will be very, very small. So in that case, this lambda will be so small, and I'll be having molecules closely packed. So because of that, voids will be less. So if our voids are less, then obviously we can actually have the assumption of continuous medium. If void space is significant, then obviously we cannot assume that we are having everywhere homogeneity. Is this point clear?
Yes, sir.
So does lambda also
Question-
depend on L?
That also depends upon,
L.
yes, L. If see what will be happening in actual practice, if you see, lambda is something which is almost fixed, okay, for a given situation. For example, if you have air at atmospheric pressure and atmospheric temperature, then for air there will be some fixed mean free path. Now it is up to you if you are taking a system of micrometer size or millimeter size, meter size or kilometer size. So if you take air in the entire size of say 1 meter or 2 meter system, then obviously with reference to that 2 meter, value of lambda which is in nanometers, that will be almost negligible. So there we can consider that whatever void gaps are there, these are almost negligible with reference to the entire size of the system. If you talk about a system at micrometer level, then obviously the arrangement of the molecular in nanoscale may lead to significant void space, and we cannot apply the condition of homogeneity. Am I clear?
Sir, will lambda also vary if L vary?
No. Lambda, yes, it will be varying, but not much. For example, if you take a small container and if you take a big container, okay. Now, if pressure and temperature are kept same, then lambda in both the situations will be almost of same order. However, L is changing. Am I clear now, Lavis?
Yes, sir.
Okay, then next question is, in open system, is there any change in mass? Yes, in open system, there may be change in mass, as I have told you. So if I draw example of an open system. For example, if mass is entering at say dm1 by dt rate and mass is leaving say at dm2 by dt rate, and let us consider if mcv represents the mass of the control volume at any instant, then what will be happening? dm1 by dt minus dm2 by dt will be equal to dmcv by dt. So mass of the control volume will be changing depending upon the inflow and outflow condition. Is this point clear?
Sir, I want to ask, if we are boiling water over a Bunsen burner in a container, so that will
Yes.
come under open system or closed system?
If we are boiling water and if we are actually considering, so that once again it depends what boundary you want to consider for the system. Okay, so say if a boiling water container is covered from the top, okay, and if you are considering that cover also as part of the system, then it will be a closed system. And if you are not having any cover and vapor fumes are coming out, in that case, obviously, there will be mass loss from the imaginary boundary of the system. Then we will be calling it as open system. So it depends upon the situation, whatever you are considering.
Okay, sir, thank you.
Sir, we included it in the closed system when it was not covered by lid also.
Yeah, then in that case, we will be considering it as fixed mass system, because we will be saying that whatever the vapor is rising, that is nothing but being collected at the top portion of the system. Okay. Am I clear?
Yes, sir.
Okay, so next question is significance of mean free path. So I think I have already told you that mean free path is nothing but it is the average distance between the successive molecular collisions. This point is clear. So obviously at the microscopic level, what will be happening? It may happen that some molecule are traveling 1 nanometer distance in order to have collision. Some molecular may travel 2 nanometer distance. Some may travel 10 nanometer distance. So what is the overall average number we are getting? That we call as nothing but mean free path. Can you come closer to your mic?
Sir, I'm still confused about
Still confused about?
voids. The question asked by Ashutosh.
Okay, so the idea is, once again I am telling you, say if I have a container and size of this container is 1 micrometer, okay, and I have another container, size of this container is 1 meter. Now, if I say that in both cases we are having air inside, and pressure and temperature in both the situations is same, okay. So now what will be happening here? If I draw, now if I represent the molecules based on the mean free path, so what will be happening? Say this is my one molecule, this is another molecule, this is another molecule. So I am just placing these molecules in a gap equivalent to that of their mean free path, means the average distance after which they will be colliding. So this is one situation. Now if I do the similar one for a 1 meter scale, so for 1 meter scale also lambda will be almost same because we are having same conditions. So now you can see where you are having more number of molecules. Can you answer where you are having more number of molecules? Who asked this question? Can you please answer where we are having more number of molecules?
The second one.
Okay, so where we will be having more chances of collisions?
In the second box.
Okay, where we will be having less probability of finding a void space?
In the second box.
So it means, can I consider it almost homogeneous medium everywhere?
Yes, sir.
So now your doubt is cleared, or still you are having confusion?
Now my doubt is. Thank you, sir.
Okay, next question is what is thermodynamic equilibrium, and thermodynamics is applicable on other than equilibrium state. So this typical question I will not take at this point because I have not yet introduced the concept of thermodynamic equilibrium. This I will be doing in my next lecture. So probably in our next lecture, this question will be automatically answered. Is it okay? Who asked this question?
Okay, sir.
So this will be like cleared in our next doubt. Okay. What does Knudsen number signifies? Next question. So Knudsen number is something, whatever this representation I have drawn, it almost gives the same idea, because Knudsen number is nothing but equal to lambda by L. So it relates the relative comparison in between our molecular length scale and macroscopic length scale. So if macroscopic length scale is very large in comparison to molecular length scale, then obviously we will be having this second situation, whatever I have shown over here. Okay, so there we can apply the assumption of continuum. So am I clear in describing the significance of this Knudsen number?
Yes, sir.
Okay, then mean free path collision frequency, is it now clear? Next question is on mean free path. I think I have already discussed it.
Yes, sir.
Bulk property also I have discussed, how time scale affects the condition of continuum. I think I have already discussed.
Excuse me, sir.
Yeah, please.
Sir, if we have to define a system, would we
Yeah.
define it in a way that like the process that occurs at the boundary of our system, that's what will define our system? Like, is it closed or open?
Yeah, yeah.
Okay, sir.
So if across the boundary there is mass transfer, then open. If across the boundary there is no mass transfer, then close. The next question is, in microscopic study, we also considered bulk movement in second method, then how it is different from macro study. So probably I think now this question should also be clear to you, because in microscopic we are only concerned that whether our molecular distribution is significantly contributing in our system. Obviously everywhere it will be contributing, but whether the void space, whatever we are having between the molecules, these are of importance, or whether we can take the overall property as a bulk property. Okay. Then next question is about the formula Q equal to HA into T1 minus T2 in convection heat transfer. What is the value of H? Okay. So in the formula of convective heat transfer, Q equal to H into A into Ts minus Tf. This H is something which is known as convective heat transfer coefficient. So it is not part of this course. It is part of next course, which is particularly called as heat transfer. So over here, just I'll briefly tell you that if we are having a surface and it is exposed to still air, then in that case, what will be happening? There will not be, so there will be transfer of heat, but it will be at the slow pace. Okay. If we are having same temperature difference, Ts minus Tf, same surface area, but instead of still air, now if we are using a fan to flow air or to blow air over the surface of the plate, in that case, the rate of heat transfer will be fast. Okay. So this effect H actually accounts for the conditions of surroundings with which heat transfer is taking place. So depending upon that, it specifies the variation or the rate at which heat transfer is taking place. Am I clear? Those who have asked the similar question, they can reply, and others can also reply if they are clear with the question.
Excuse me, sir.
Okay, now one thing I have got in the chat, that question number 9 has been skipped. So I am going to question number 9. Yeah, so in an isolated system, if there is a mass to energy conversion or vice versa, within the system itself, there is mass energy interaction within. There is mass energy interaction within the system. So will it still be considered as systems are changing? So generally, let me tell you what happens. Now I am taking question number 9. I have actually 2-3 screens over here, so I have to move in between these two. That's why sometimes it takes time. Okay, so now what I am considering, that let us consider this as nothing but our isolated system, okay, where it is not having any mass or energy interaction with its surroundings. So obviously, inside this system, whatever the medium we will be having, that medium will be having some properties at the given state of this system. So for example, I will be having some pressure, I will be having some temperature. So this particular system state will be only defined if it is in thermodynamic equilibrium. So if it is in thermodynamic equilibrium, in that case, there will not be any process happening within the system. So because of that, at each and every point of time, it will remain at the same state. Okay, and more details about whether at a given state, why we are having system at thermodynamic equilibrium, that we will try to see in our next lecture. Is this point clear? Question 9, who asked?
Yes, sir, Sami.
Yeah, is it clear to you?
Sir, not entirely, sir.
So what I am mentioning, that when we define a thermodynamic state of the system, at that time we consider that our system is in thermodynamic equilibrium. If system is in thermodynamic equilibrium, then within the system we will be having everywhere uniform property. If within the system we are having everywhere uniform property, then there will not be any change in property of the system. Okay, so that's why inside an isolated system, no process should take place if we are able to specify its state, because state is directly related to the thermodynamic equilibrium. Am I clear?
Yes, sir. Thank you, sir.
More details we will study in our next lecture. Then next question is, which number I'll be now going to? 22. Are both real and imaginary boundaries considered of zero thickness? Yes, both are of zero thickness only. So in real, there may be actually some thickness, but for our analysis point of view, we will be considering it of zero thickness only. Okay. Then next question is, this question is clear?
Yes, sir.
Yes, sir.
Next is, for a closed system,
Yes.
should the boundary of the system be always real? Yes, means it once again depends, because we may have a situation where we are actually heating water inside a container. So if we are not considering the effect of boiling, if we are only doing the sensible heating, then obviously the mass of the water inside the container will remain fixed. And in that situation, though, from 3 sides we will be having real boundary, but from the top we will be having only an imaginary boundary. So it is not always true that for closed system boundary has to be real only. So this part is clear?
Excuse me, sir.
Yeah, please.
So if we'll not have the boundary real, then the mass, there will be transfer of mass.
If we are only doing the sensible heating, for example, under atmospheric pressure, if we are heating water below 100 degrees Celsius, in that case there will not be any mass transfer if we are neglecting the effect of evaporation.
Yes, sir.
This point is clear?
Yes, sir.
Okay, the next question is, sir, if we mix hot water and cold water, then is it convection or conduction? So it now once again depends. If so, as you are talking about mixing, then obviously if we are mixing these two, we have to we will be inducing some type of flow in order to mix each other. So we will be having nothing but bulk motion between the two mediums. So mode of heat transfer we can consider as convection. Okay. Is this point clear?
Yes, sir.
The next question is, how can we assume that there is no empty space in container, because we are estimating number of molecules by calculating the volume of container, but practically there should be open spaces inside container. Obviously, practically there may be open spaces, but these open spaces will be negligible if we compare a large room, large container. Okay, so particularly if we consider the engineering length scale, so probably whatever the illustration I have presented in the previous figure, with that this question is, I think, already answered. Am I clear with question number 25? Yeah, evaporation occurs at every temperature, but what will be happening in actual practice, the mass transfer because of evaporation will be very happening at very slow rate. So because of that, within the time frame where we are analyzing our system, we may consider that mass transfer during that time frame is actually negligible. Ankit, is this clear? Okay, now next question is, how can we assume that there is no, that is done? Then 26 is, how are the properties of void spaces and bulk different? As there is no method to measure the temperature in the interatomic void. Obviously, so in the interatomic void, as there will not be any medium, so there we will be saying that as we are not having any physical matter present, so obviously corresponding to that, we will not be having any value of property available at that particular location. Okay.
Yes, sir.
The next question is, you told that thermodynamics can't tell about the mode of heat transfer. Then how do we come to know about the mode of? So whatever the mode of heat transfer, we are now telling that you are actually telling from your earlier knowledge of 12th class, where you have studied about different modes of heat transfer. If you want to know in details about the modes of heat transfer, then we have to go for a course on heat transfer. Okay, so what we are doing at present, we are just saying from our earlier knowledge that how we are having or what mode of heat transfer is happening. But however, if we have to go for detailed analysis of the system by considering what is the rate of heat transfer and how much time it is taking for the heat transfer to take place, that we will not be able to obtain from this knowledge of thermodynamics.
Okay, sir.
Is there any other question?
Yes, sir. I want to ask one question.
Yeah, please go ahead.
Sir, in yesterday's lecture, you told us about the Newton's law of cooling. In that, you wrote Q, but there should be dQ by dt.
Yeah, so actually what we do, so that is what the difference of notation is coming. Basically, I have referred there Q to the rate of heat transfer. Okay. Rather than the amount of heat transfer, I am calling that Q as rate of heat transfer. So when we study the heat transfer subject in our undergraduate level, so there normally we try to follow symbol Q for rate of heat transfer. Okay.
So thank you, sir.
Any other question? Fundamentals of thermodynamics referred by. Yeah. So one more thing, like whatever the lecture material I am taking, all the lectures I am uploading on Moodle. So all of you, please get familiar with the Moodle. Go to the Moodle. If you say I'm not able to connect during the time of the lecture due to some internet issue, so you can listen to the recorded version of the lecture. So I am uploading the lectures in 3 different versions. So whatever I am scribing on this board, that also I am uploading. Apart from that, recorded video is also being uploaded. And apart from that, I am asking one of my TA to prepare the transcript of my recorded lecture, and that also I am uploading. All of you please go and to your Moodle page and try to see the material over. Yeah, can we buy any of the? Yeah, if you want to buy, yes, you can go for any of the textbook, either Sontag or Sanjay. Okay. So if there is no further query, then I want to stop this session. Is it okay?
Yes, sir.